Hello, we're following up with our exponential functions. We're going to do 3 more applications so we can see these exponential functions in action. So for number 5 here, we have a census conducted, we have the initial population, and then the growth rate, the 2.03%. So the first thing we want to do is write an equation to model the situation. So we're going to use our initial amount of 3,929,214 as your A value. Our growth rate is 1 plus R, but we do need to move that decimal over, so it's 0.0203. And then since it's just an equation here, we are going to use T or X for your exponent. Also, you can absolutely simplify this. In fact, if you just want to jump to the 3929214 times 1.0203 to the T for your equation, feel free to just start jumping to that. Okay, so then we're going to use our equation to predict the population in 1843. Now, our initial year was 1790, so we really need to figure out how long it's been in the year 1843 since 1790. So we're looking at a 53-year gap. So that is going to be what we use for our X value. And we're going to plug in 53 here for our time. And type that all in on your calculator. You get 113,99444.16. But since we're talking about people here, we're not going to have any portions of people. We're just going to use 113,99444 for our estimate. Okay, let's go ahead and take a look at number 6. If you want to try it first by pausing the video and then just checking your answer, that's absolutely fine. For this one, the 14.7 is your initial amount. That's your A value. We have a decrease, which means we are using the subtraction. So the 20% would be shown like this, 1 minus 0.2. So our equation is 14.7 times 0.8 to the x. So you could go ahead and graph this if you'd like to and take a look at what this graph looks like. You will see that decay function. We want to figure out the atmospheric pressure at an altitude of 13 miles. Now, we're not really using 0 and 50 at all. It's just kind of the context here. It's saying after 50 miles, this atmospheric pressure doesn't apply anymore. So we couldn't have you figure out an altitude of like 80 miles because then it's not in the applicable part of this. So for this one, we're just going to go ahead and type in 14.7 times 0.8 to the 13th. And when you do that, you get 0.808. And our units for this one is pounds per square inch. Okay, our last one here, a different application. We have a depreciation. Anything that is implying like decrease means you're going to use the minus. So we want to know how much a $15,000 initial mower would be after 5 years if it's only worth 90% year after year. Or you could do 1 minus 0.1 for your decay factor and get 0.9 there. So we type that in on our calculator, we get $8,857.35. So for the next one, we want to know when the mower will be worth 2,000. This is our ending amount. This is our Y value. So we're going to plug in 2,000 for our Y value. We're going to keep the same 15,000 and keep the same 0.9. But what we don't know is we don't know the time. So right now, we don't know how to solve this when you have the x up as the exponent. So what we're going to do is we're going to type this first part into y1 and the second part into y2. We're going to end up with a graph that looks like this and then like this. And what we want to do is we want to figure out where these are equal to each other. So you are going to have to change your scale a little bit. So I'm going to go ahead and take a look at this. Here is y equals 2,000. And y equals 15,000 times 0.9 to the x. So my x values here, you can go up to like 100 or even 20 should be enough. For your y values, you want to make it past 2000 because now you can see that this intersection point here is 19.124 comma 2000. So 19.124 comma 2000 means that our y value will be 2000 in about 19.12 years. So a different application of this exponential function. So thank you very much for listening. I hope this helps. Let me know if you have any questions.